Okay, now the third section of our talk, I will apply what we have in the differential formulation of Maxwell equation to derive the wave equation of electromagnetic wave. Before that, I would like to introduce one further notations. Here, remember that grade acts like a vector. Therefore, you may wonder, if I combine two of them as an inner product, could it generate a scalar? The answer is yes. So what I will do is to write symbolically the grade dot grade. Now grade dot grade, according to our intuition, it will be partial x plus partial y plus partial z. And partial x is just doing the partial differentiation twice, so it would be partial square partial x square plus partial square partial y square plus partial square partial z square. We will define this as a Laplacian, or sometimes you'll call it just according to the symbol, it's grade square. But it has a more, because it was originally used by Laplace, one of the greatest mathematicians in the 19th century. Therefore, we call this thing as Laplacian. And remember, just like grade, this Laplacian is also just an operation. So for it to make any sense, this operation has to add on something, operate on something. So usually it is used to act on a scalar function. So the Laplacian square would be defined as u partial square u partial x square plus partial square u partial y square plus partial square u partial z square. This operation is called Laplacian. Actually, you probably have met it in your general physics or electromagnetic courses, because it could be used to write an equation for electric potential. Remember, the electric potential, we can use the electric potential to derive the electric field. E is equal to the grade of electric potential. And we also know from the Gauss's law, the divergence of electric field is equal to rho over epsilon square. So you just plug in the first formula into the second one, you get the divergence of E is equal to the divergence of grade V. And divergence of grade is just what we have written here, the grade dot grade. Okay, so it is Laplacian square V. Actually, you can write down all the detailed formulation to show it is indeed the Laplacian square, Laplacian or grade square V. Then, therefore, the Laplacian V is equal to rho over epsilon 0. Okay, so this is the equation that is satisfied by the electric potential in electrostatics. Of course, if it is not electrostatic, instead the magnetic field is changing, then the electric field cannot be written in terms of electric potential. Okay, then this equation will not be true anymore. However, in electrostatic, this Laplacian equation is all you have to solve to find the answer almost of every question you can ask in electrostatics. Okay, so this is Laplacian equation, and it will play some role in our future discussion in the partial differential equation. Okay. Oh, and of course, forgot to mention it is a partial differential equation, because here the equation is actually involve the partial differentiation of a function we want to solve with respect to x, y, and z. Okay. And there's no time because it's just static, but it's still a partial differential equation, just like the wave equation we are going to write down very soon. Okay, now we would like to use the differential Maxwell equation to derive the electromagnetic wave equation. It is easy, only one page, maybe two, because we need to derive a formula that we will use in this derivation. So maybe 2 pages. And then we can get the wave equation. That's the power of the differential Maxwell equation. Okay, it's easy to calculate and easy to get to derive further result. So let's start with the Maxwell equation in vacuum. In vacuum, there is no charge, there is no current, so you get rid of rho, you get rid of J. The only thing you have is the partial the partial B partial T and partial E partial T. Okay, but it indicates that the partial B partial T, the changing of magnetic field and the changing of electric field could act almost like a source of the electromagnetic field. Okay, so as I have mentioned in my second section, these two terms are very, very important because, again, it could act as a source when in vacuum. Okay, we don't really need the rho, the charge and current everywhere in space for the electric field to be generated. However, you can just ask your electric field and magnetic field change with time, then it will generate each other in turn. That's what we are going to derive an equation for this kind of phenomenon. Okay, now we got 4 differential equation. Not differential. We got 4 differential Maxwell equation. Then the third one says that the spatial change of electric field is interrelated to the temporal. Temporal means the time change of the magnetic field. Therefore, I can take a curl of the whole thing. By doing it, the left-hand side give you the curl of E. We will have an expression for this complicated calculation later. However, we know that this must be equal to minus curl B. I should say minus curl the partial B, partial T. But I can interchange the order of time derivation and the space derivation. So this part will become, you plug in, it becomes, it becomes the curl B. We look at the right hand side first and we'll take care of the left hand side. The right hand side will become, if I change the order of time derivative and the spatial derivative, it will become curl B taking a time derivative. The point is, this curl B actually is related to, by this force as a force equation, to the time derivative of E. Okay, so if you plug in the force equation into this curl B, you get the second derivative of time. So the right hand side could be easily written as minus mu 0 epsilon 0 E taking second derivative of time. Now let's take care of the left hand side. The left hand side is a very complicated form of curl E. This curl E is equal to grade divergence of F minus Laplacian F. Why? I have a derivation in the second, in the next page. I will derive first A cross B cross C because this is what we have here. If you replace this grade by A and this grade by B, then this is what we will have as A cross B cross C. The formula for this complicated cross operation is very useful in your electromagnetism courses and probably also in your mechanics courses. Therefore, let's derive it carefully so that you can use in your future. So A cross B cross C is not very complicated. Just 1 page of derivation will be enough. There are 2 kinds of derivation. I'll use the first, the easier kind to show you how the formula comes out. Let's calculate the components directly. Most of the time, you can always calculate for a formula about vectors. You can always calculate the components. Here, I first write down the z components of this complex vector form. That is A cross B cross C, the z component. It is easy to write out what this component is. It is equal to A. If you treat the B cross C as a vector, then this expression equals AX times B cross C, the y component, minus AY, B cross C, the x component. You can consult your definition of cross product to see that this is true. Then the second the second cross product could also be expanded in terms of components. So B cross C, the y components, equal to BZCX minus BXCZ. The second one looks similar. So the x component of B cross C equals BYCZ minus BZCY. Okay, and so that's almost the final result. We can get as far as we could. However, this form is not very useful. However, you can take a look and see that if you look at BZ here and BZ here, you find that the thing it times is AX CX. Here it is AY CY. Okay, so how about we just group them together and write as BZ times AX CX plus AY CY. What in my mind is that their components are the same. It is X matching X, Y matching Y. Sorry, too fast. Okay, so I will group these two terms together. How about the rest? The rest, it is this term and this term. They all consist of CZ. So I'll pull out the CZ, and what's left is AX BX plus AY BY. So it's almost the same thing as the first term, X match X, Y match Y. Therefore, it looks like part of the inner product of A and B. What is missing is AZ, BZ. Wait, so what is missing here is AZ, CZ. So the missing terms are the same in both terms, okay? So I can add a BZ, AZ, CZ to the first term and subtract it from the second term, AZ, BZ, CZ, so that I have a complete inner product and complete inner product. So this whole thing can be written as BZ times A dot C minus CZ times A dot B. And it's the Z component corresponding to what we are calculating. It is the Z component of A cross B cross C. So it tells you that I can do the same for X and Y and Z to form a vector formula. So that means the three components of this will be equal to the three components of the whole thing. Remember, A dot C is a scalar. So for Z component of this, it will be equal to the Z component of B times this scalar minus the Z component of C times this scalar. Let's do it again. So the Y component of this vector will be the Y component of B times scalar minus the scalar times the Y component of C. Okay, therefore, this is the form of the formula. Okay, so you plug in, substitute this A by its grade vector, B by another grade vector, then this thing will become grade dot F minus grade dot grade F. And grade dot grade is just the Laplacian. Okay, so we arrive at the formula we need to do the electromagnetic wave equation. Okay, so there is another derivation of this formula, but it is quite abstract. So I listed it here so that you can take a look, and if you have you will use it later, then you can take a closer look. Okay, so I have this expression. The curl of curl f equal to grade diff f minus Laplacian f. So I can plug in to calculate the left-hand side of what I had earlier. So this term could be expressed as the grade diff e minus Laplacian e. The point is, now the first term of the right-hand side actually vanish because the divergence of E in vacuum is equal to 0. There's no charge in the space in vacuum, therefore there is no divergence of electric field. So the first term vanish, so what's left is a Laplacian. So put everything together, I arrive at a very, very simple equation, partial differential equation. The left-hand side, the Laplacian E equal to mu 0 epsilon 0 times the partial square electric field partial t square. Okay, so that's the wave equation for electric field. I will turn it into a form familiar with us later in next page. So, but now I will tell you this equation is not only satisfied by electric field. You may ask, how about magnetic field? Yes, if you are asking about the magnetic field, I can derive an equation for the magnetic field in vacuum. Again, the derivation is quite similar to what we have for actually almost identical to what we have for electric field. Here, we use the third term, the fourth term, and taking a curl of both sides. And the left-hand side could be written just using the same formula as grade diff b minus Laplacian b. Diff b, according to, the arrow is pointing to the wrong equation. It should be from here. Diff b equal to 0, so the first term also vanish. So we are left with a Laplacian on the left-hand side. How about the right-hand side? On the right-hand side, we have curl partial e partial t. Again, I can interchange the order of the two derivatives, so this term becomes curl e partial t. But curl e has a formula for it. It is related to the time change, the rate of change of b. So if you plug in this equation, then we got it is equal to b partial square b partial t square. Okay, therefore taking everything together, you got the Laplacian magnetic field equal to mu 0 epsilon 0 partial square b partial t square. So compared to the earlier page, the equation for electric field is totally the same as the equation for magnetic field, which is a wave equation for electromagnetic field in vacuum. It doesn't look like the equation we are seeing in our earlier derivation of string or couple oscillation. But in that case, the space has only one dimension. So if what we want to reduce the wave equation of electromagnetic wave to one dimension, what we do usually is to restrict restrict the propagation of our wave in the z direction. Okay, so in the x direction, sorry. So we will consider a special version of electromagnetic wave with the electric field in the y direction and the magnetic field in the z direction. I list the diagram here. So electric field in the y direction, we call it EY, and magnetic field in the z direction, we call it BZ. And both of them will depend on only x. because the wave will move in the x direction. Okay, and therefore the field will be a constant on the YZ plane. Therefore, this kind of wave is always called the plane wave. And in this case, because the y is only in the EY direction, so we can restrict our calculation, the Laplacian, to EY. Originally, the equation are for 3 components of electric field, but because the electric field now has only y component, so we restrict it to EY. And the derivative originally has 3 components. However, the EY only depends on x. Therefore, partial y and partial z is equal to 0. Therefore, we are only left with partial square EY, partial x squared on the left-hand side. On the right-hand side, you pick out the EY because that's the only thing that exists. So it is partial square EY partial t squared times mu 0 epsilon 0 equals EY partial square EY partial x squared. So if you treat this EY, and it's the same thing for BZ. So let's not just go into detail here. So BZ satisfy almost exactly the same equation as EY. And it is easy to compare it to the wave equation we have already derived in the earlier case. This is the wave equation we have derived. Remember, here we have a v, which should be the wave velocity. And compared to the 2 equations, you can easily find the speed of electromagnetic waves. First of all, the electromagnetic field in the space actually undergoes the same disturbances as the waves occurs in a string. Okay, so that's why we call it electromagnetic wave. And the speed of the wave, or wave speed, is equal to 1 over square root of mu 0 epsilon 0. If you calculate this number, we know that mu 0 is about 1.26 times 10 to the minus 6. Epsilon 0 is about 8.85 times 10 to the minus 12. You can see that we got a 10 to the minus 18 in the denominator. Taking the square root, it comes to 10 to the minus 9. In reverse, it becomes 10 to the minus 10 to the 9th. However, there is a 1 times a, so it's about square root of it is about 3. So it's 1/3. That means it is equal to 0.3. Put everything together, we arrive at the speed of electromagnetic wave, 3 times 10 to the 8th meter per second. So everybody could see it actually speed of light. So by a single stroke, Maxwell derived there is a certain wave that could travel through the vacuum without anything in the medium. 没有任何的这个介质 ，OK？ 之前所有的波都有一个介质在那个地方。But for electromagnetic wave, we don't need a medium. It is actually disturbances of the electric field and magnetic field. Okay, and even more surprising, light is one kind of electromagnetic field. So that in one stroke, Maxwell unified electromagnetism and optics. It's almost the highest point of physics in 19th century. That's for sure. Okay, let's quote the original words of Maxwell in his paper. Here he say, the agreement, here he lists the speed of light he calculated, and the speed of light, the speed of electromagnetic wave he derived, and the speed of light observed in experiment, and see they are identical to each other. And Maxwell say, the agreement of the results seem to show that light and magnetism are affections of the same substance, and that light is an electromagnetic disturbance propagated through the field according to electromagnetic laws. Okay, so this is beautiful and this is very important. Remember again, we are going to come back to the same we are going to come back to this thing next semester. We'll start to solve this equation, the wave equation. Okay, so in this semester, we have derived the wave equation in 3 ways. The first time we derive it through the continuum limit of coupled oscillation, and then we derive it for the string, and then now I derive it from the electromagnetic law, the Maxwell equation. Okay, so you can see that these 3 different kind of phenomena are about different physical system. However, they all observe the same mathematical equation. And so we expect they can be solved in the same way. That will be the topic and the point, the highlight of our second semester. So see you next term.